Welcome to this Ansys how-to video. Modal analysis is used to determine the vibration characteristics. For example, natural frequencies and mode shapes of a structure under free vibration. Note that free vibration means that there are no external loads. So why do we need to know the vibration characteristics of a structure? In some designs, an engineer may wish to avoid having the natural frequencies of a structure in a given excitation frequency range to prevent the response from being amplified. However, there can be other cases, such as the design of a piezoelectric transducers, where we might wish to excite the system at resonance. After performing a modal analysis of a structure, we may consider modifying the structure to shift the natural frequencies to meet our design objectives. And this video helps to understand how to use simulation to gain more insight into the design and revise it based on modal analysis results. Ready? Let's go! Using modal analysis, we can get the natural frequencies of the structure experiencing free vibrations. To determine the natural frequencies of the structure, its mass and stiffness play important roles in the modal analysis. As seen in this equation, the stiffness of the structure is directly proportional to, and the mass is inversely proportional to the natural frequency of the structure. So if we have to alter the natural frequencies of the structure, these are the two terms we can adjust. When we perform the modal analysis, we generally get multiple modes or frequencies for a given structure. Out of all these modes, it is important to determine the most significant mode. But how can we identify such mode? This can be done by understanding the participation factors for the various modes. Once the modal analysis is solved, the participation factor summary can be found under Solution Information or Solution Output drop-down list. If you look closely, it lists all the modes, their corresponding frequencies, and their participation factors in each direction. Looking at the ratios of participation factors, we can determine which mode is the most significant. In this table, the first mode has the highest participation factor in the z direction. Hence, we should focus on this mode and its corresponding frequency, as it may get excited under external loads aligned with the global z direction. And if the natural frequency of this mode falls within the excitation frequency range, it may undergo resonance. Now, after determining the significant mode and its natural frequency, we need to make sure that the structure does not vibrate in the unwanted range. Hence, we want to change its natural frequency. As discussed earlier, the natural frequency depends on two factors, mass and stiffness. So to change the natural frequency, we need to alter either mass or stiffness or both. If the stiffness is increased, it increases the natural frequency, and if the mass is increased, it decreases the natural frequency. To help us with this decision, the strain energy density output is very useful. Regions of high strain energy density indicate the locations which should be stiffened to increase the frequency for that particular mode. Conversely, areas of low strain energy density are candidates for material removal that may not drastically decrease the frequency of that specific mode. Keep in mind that for each mode, the strain energy density distribution may differ, so we should understand that any change to a design can affect multiple modes differently. Note that we need to extract the strain energy density instead of strain energy, because the strain energy density term is independent of element size, while strain energy is not. Now, let us try to understand this with a simple example. Here, we're looking at a plastic bracket, which is assumed to be wedged between two other parts from the top and side surfaces. Frictionless supports are added to these two surfaces where the connector mates with other parts. For the surfaces of these holes, radial-only cylindrical constraints are added, representing that the parts are pinned together and rotation around the axis is allowed for these surfaces. As we mentioned before, modal analysis does not consider any excitation, so no loads will be allowed in the settings here. Then, in the analysis setting, We specify that the maximum number of modes to find is 10 for this analysis. And also in output controls, we need to turn on volume and energy, since we need to evaluate strain energy density results after the modal analysis gets solved. Before solving it, let's assume that for this structure, one of the design requirements is to avoid natural frequencies under 700 Hz, because the frequency of the excitation loads will be in this range when the structure is in operation. Now, let's solve for the modal results to see if the original design meets this requirement. Alright, the solving process is done. Click on Solution from the outline. We can see the 10 natural frequencies are found and listed here. The lowest natural frequency is 664 Hz, and the highest natural frequency found is 4268 Hz. Apparently, the first natural frequency is undesirable for this design as we want to avoid natural frequencies under 700 Hz. Let's evaluate the result and see if we can come up with an idea to revise the design. First, we can have a look at the mode shapes corresponding to these natural frequencies. Select all the natural frequencies in the list, right mouse click, then click on Create Mode Shape Results. The mode shape results will show up under the solution. We can see that the first mode is mainly bending in the Z direction. We also want to know how this mode could contribute to the structural behavior. Is it a negligible mode, or is it a mode that may play a key role? Such information can be found from the Modal Participation Factor table. Click on Solution Information from the outline, change the solution output to Participation Factor Summary. Here we can see that in Z direction, the participation factor of mode 1 is the highest. This means that if there's an excitation in Z direction, mode 1 will be easily activated and will play a key role. Besides the mode shape, we can also evaluate the strain energy density plot, which can tell us where the structure has large strain at this natural frequency. Strain energy density is defined as strain energy per volume. Both strain energy and volume outputs are user-defined results in Ansys. To access user-defined results, we can click on Solution from the outline, then click on Worksheet from the ribbon. All the available user-defined results are listed here. We can find volume and potential energy in the list. Note that potential energy is equivalent to strain energy. Now, right mouse click on the row of potential energy and click on Create User-Defined Results. A new result is added under the solution. Click on this item and go to the expression. It says Energy Potential. Since we want strain energy density, we need to divide this value by the volume. We can directly edit the expression there to get strain energy density. Evaluate the results and the contour plot is obtained. One tip here is if we want to create user-defined results for all the modes, we can simply right mouse click on the results and click on Create Results at All Sets. Here, let's focus on mode 1. As we mentioned, strain energy density gives us an idea of where the structure has large strain at this natural frequency. By stiffening that area, we can increase frequency of that particular mode. Conversely, regions of low strain energy density may be candidates for removal of material without adversely affecting the frequency for that specific mode. In this case, the objective is to avoid natural frequency under 700 Hz. So basically, we want to stiffen the structure so that to increase the frequency. We can see that strain energy density is high on the top and bottom beam. Increasing the stiffness around this area will be the right way to go. Now, I can think of two strategies to do so. Strategy 1 is to add a rib linking the top and the bottom beam where large strain energy density areas are. Strategy 2 is to simply increase the thickness of the top and bottom beam in Z direction. Which one is the right way to go with, or maybe both of them are good choices? Now, let's observe the mode shape again. Clearly, it's mainly bending deformation in Z direction. This tells us that the strategy 1 is not an effective method, because adding a rib can stiffen the vertical direction of the structure effectively, but will not help much in increasing the moment of inertia to resist bending in the z direction. On the other hand, the second strategy of increasing the thickness of the beam in the z direction will be much more effective to reduce bending deformation in z direction. The rule of thumb we learn from here is that we need to look both the strain energy density plot and the mold shape to decide where and in what direction the structure needs to be stiffened. In this case, we will increase the thickness of all the beams in z direction. Note that for the short middle rib, the strain energy density plot didn't indicate this part needed to be stiffened. The reason we also add material in that location is for an aesthetically pleasing design and for an easy manufacturability. Here we have a design with the thickness of the beam in z direction increased by 4 mm. Solving the modal analysis, you will find that the first natural frequency is increased to 812 Hz. Now, we successfully avoided any natural frequency under 700 Hz. In summary, we now know the importance of the modal analysis. It is a very useful approach to determine the vibration characteristics, the natural frequencies, and mold shapes of the structure. Once we extract the modes of the structure under free vibration, the participation factors can be instrumental to help us identify the significant modes that we need to focus on. And finally, the strain energy density output helps to provide insight regarding the structural behavior in design. That is, where to add materials to increase the stiffness or where to remove materials to reduce the mass. Thus, the modal analysis results, though being relative, give us information regarding the dynamics response of the system well before we perform more computational expensive dynamic simulations. The modal analysis can be used as a quick way to improve the design at the early stage. If you find this video helpful, please like, comment, and subscribe. To find more information about modal analysis or other topics, check out our channel for more how-to videos and visit ansys.com/courses today.